Okay, so 6.2 design example. Let the system have this plant transfer function, fourth order. Design a P lead controller such that the closed loop settling time is about 0.8 of a second and the overshoot is about 15%. So that's our, looks like I went even more hardcore. I went down to 0.4 seconds. 0.4 seconds, and then I went to 10% overshoot because I felt like it, I guess. I don't know why, but I should have changed that. So we use MATLAB for the design. First, we must determine what the specified transient response criteria imply for the locations of our closed loop poles. Let one of the desired pole locations be called psi. The transient response performance criteria are given here. I showed before how this implies a specific psi depending on the percent overshoot and settling time. And I define it as a function here. It's pretty useful to use that function. Comes up a lot that we'll want settling time and percent overshoot as our two requirements. So we want a psi at -10 plus J 13.6. I got really tired of always doing the trigonometry by hand for this. So Nice is like always doing that in the textbook, which is totally fine. But I just thought I'd do it once in general and then just write the formula and not have to do it again every time. Yeah. I, for one, screw up hand-done trigonometry pretty regularly. So earlier I was having a really hard time remembering if if sine theta equals cosine theta plus pi over 2 or minus pi over 2. It took me a few minutes to actually figure that out. And, you know, there was a time when I would have known that off the top of my head, but now I had to look at the unit circle, reason, different points, plugging them in. Okay. So there we go. There's our design point. So -10 plus J 13.6. This was a root locus without compensation. -10 plus J6, that's like right here, right? Or maybe a little lower. It's like right here. We're not on the root locus there. So we're going to need to have some derivative compensation or some lead compensation, which is what we'll be doing. So P control. First, we try to get as close as possible to psi using the root locus. We can't really get close. We can at least meet our percent overshoot spec if we choose a gain of 1.1. So I did that. And I didn't even bother trying to simulate it because I was like, we're going to be way off anyways. Let's go ahead and give this a shot. Before we put in our compensator, our second order approximation is probably okay, right? Maybe it's not awesome, but it's going to be decent. So we're thinking that, you know, we probably will need our root locus to go through this point or pretty close to it to meet our design specs or design requirements. Okay, so lead compensation. I chose, let's arbitrarily choose PC to be -40. Then from these equations, we can compute theta C and ZC. Now, I ended up going back and setting it to -40, -100, and -400. So I was like, okay, -40, and it worked just fine. But I wanted to show you guys what would happen if I had chosen 3 other values. So I chose 3 other values. From the very beginning, I just calculated it 3 different cases. So theta C contribution is the same that I need each time. I need to contribute that many degrees of phase. And the pole phase contribution for these different cases were 24, 8, and 2 degrees. And then the 0 compensator locations that were required based on the trigonometry, I listed below here. So the 0 is pretty close to the real axis here, and then it gets further away as I move the pole outward, leftward. Okay. By construction, psi is on the root locus, so we can find K2 directly from equation 6.2. So I have a little for loop to do it for each of the pole locations. I use the eval fr function to compute what is g of psi, right? So that's the one of the things we have to compute is what is g of psi. I would rather use the built-in MATLAB function to do that for me, so I use that. Gives me these three gains. Let's compute the closed loop controller. I have lag in there. It should be C lead, right? I kept writing lag every time I meant lead. It was great. So GP lead. I create a model array here. So a model array, remember, is an array of transfer function models or state space models or different things in MATLAB. So this is a model array. They're not super easy to work with, but they're okay. They let you do the same. They create a bunch of different transfer functions, an array of transfer functions. So then we just simulate. I wanted to do the step, and then I wanted to do for each of the cases, what was the step response. So I had to do the P case separately outside the loop, and I got these as my three. So first things first. With P control, I was out here in the blue, right? So with P control, and with all of them, our steady state error sucks. Steady state error is terrible. So we're going to probably want to do lag on this at some point. Or, lag on this. So we're going to do lead, though, to fix the transient response issue, which is to say that we wanted it to be down around 0.4 seconds for the settling time and 10% overshoot, whereas we're definitely over that for our settling time in the P control, and it looks like also overshoots too big. So we hopefully fixed that. We have these three different cases. So in all three cases, it looks like our settling times improved. Notice that the steady state error is quite a bit different for these different cases, right? So the one here was with the compensator pole at -40. This one is the compensator pole, the furthest one out, which was like -400, I think. So this steady state error was a lot better for that one. But they all look like they pretty much meet the transient requirements. Let's actually use step info to decide how we did. So for P control, settling time was 0.9 seconds, much too long. Percent overshoot was 13.6. Now, when I chose my PC at -40, remember how close that 0 was to the imaginary axis? It was at like -1 point something. So that's really going to mess up my transient response, and so that's potentially what gave us this. So settling time was even longer technically, which is a little unintuitive because it looked better, but it has this weird long tail on it that 0 is essentially causing. So we have a kind of a funky long tail here that it, technically by the definition of steady state error, or definition of settling time, it takes too long to get inside the bounds. So that one ends up being bad news. Even though it looks like it's faster to settle than the blue one, technically it takes longer. And the percent overshoot's terrible, 66%. I mean, that we see it, the steady state error or the steady state value is like 0.2, and it goes up to over 0.3. So the overshoot's way too big. Okay. So what we can see is that if we move that pole out to negative 100, we get a settling time that matches our spec, and the percent overshoot's tighter than our spec, right? Both of these are actually tighter than our spec, 0.4 and 10% for overshoot. So we exceed our, usually when you have a specified overshoot or settling time, usually those are maximum values. So you can assume that going less than that's good. You don't want to go drastically less than that because you're probably using more control effort than you need to in that case. But being, 0.3 under, 0.03 under 0.4 is pretty good, and being at 7% instead of 10% is pretty good. So pretty good there. And similar transient response characteristics for the negative 400 location. So choosing those locations, they do affect the transient and the steady state responses, even though they all go through the same design point on the root locus. So it's good to keep that in mind. So the first one's problematic. Second order approximation is significantly violated from that 0. We could also tune the gain. So one thing we could do now is try messing with the gain and see if one of these two cases came out to be a little closer by adjusting that gain a little bit. But they're both pretty good. Like either one of those would be very good designs. Okay. So that's pretty much the process of designing these things. Do you guys have any questions, concerns? Anything you want to get off your chest? Just for the internet? Any
Now I noticed that the ones that were similarly good, the minus 100 and the minus 400.
Yeah.
Now, dealing with, I understand that the settlement, the percent overshoot is changing a little bit. Is there any other effect that drastic of a change? Because it was like minus 100 versus minus 400.
Yeah, the most significant effect it had on the response was the steady state error, right? So this was minus 40, the pole location there. This was the yellow one is the pole at minus 100. So these minus 100. So these steady state error values, so none of them is great though, right? Because this should be getting up to 1. And they're stopping it, even the best ones, below 0.6. So steady state error is big in all three cases. But it's actually better for this one. So this one, we're in a nice design space when improvements in steady state error and improvements of transient response go hand in hand. Sometimes they're opposed. So you improve one and the other one it is worse. And then one of them, if you flip it, then you're fighting each other. So then often you have to trade off between two parameters or two requirements. In this case, the further out you got, the better your steady state error got. So.
Okay. So even though the percent overshoot was a little bit higher on that minus 400.
Yeah.
Versus the minus 100, the minus 400 is still a better design variable.
Yeah, this one, you're right. So the percent overshoot, really the settling times are equivalent. The percent overshoots are essentially equivalent too. So in terms of transient response, they both meet spec just fine. Either of these would be good. In terms of steady state error, really none of them is going to give us all the steady state error improvement we need. We're going to need a lag compensator. But the negative 400 location was best for that. So I would probably go with the negative 400 location. Now, there are some other considerations that would be more downstream than this. You'd probably you'd have to watch out for a consideration that we haven't talked a lot about yet, is how much control effort will be required. So if you were to simulate the step response, but then see, in order to do the step response, like how much, we didn't even say what the input was to the system, so our transfer function could have had like a force input, say. Well, maybe in order to make this, to have the step function respond, we would have needed to put in like 5 million newtons or something to make this happen. Well, our actual actuator probably couldn't provide that, and so we would have to adjust what our design was to limit our control effort that goes in. So what the controller puts out in terms of control effort is also a design consideration we haven't really talked a lot about yet. But there might be a difference. So if you choose this one versus the other one, there might be a control effort difference. You might need to take that into account. So the design, I mean, right now we're limited mostly to transient response, steady state error response, or steady state error, and stability. Those are mainly the considerations we're looking at. But we're also interested to know, like, okay, if you only have, 300 newtons of force that you can apply max, we're interested to keep any common situations that the controller would, anytime there's a step change in our command, we wouldn't want to be like exceeding that. It's called saturating your actuator. I mean, it's common that we'll operate in saturation in certain instances for our actuator, but if you do that, the performance is going to suffer. So say you run into that problem here where you're like, oh yeah, put in 5 million newtons, and it's like, well, I only have 500 newtons, so that's what I'll put in. Well, probably your response will be slower, right? And that might affect your predictions in terms of your performance. So dealing with saturation is a little bit tricky, but we'll talk about some ways to deal with it in the future. For now, we're just dealing with steady state error, transient response, and stability, though. Yeah.
In our example, how do we check the validity of the second order approximation?
Yeah, so there are a couple ways you can do it. So you can do it sort of a priori without actually checking the validity of it in terms of your performance by just saying, are there any zeros or poles that are going to be nearby my dominant poles? So you can do it from that perspective by going back to your root locus and then saying, okay, I'm putting in a compensator pole here or further out for the other cases, PC. And then the zeros are going to be in here, in this region, okay? If I put a 0 in this region, that's going to affect my second order approximation quite a bit, right? So I would say that for this problem, second order approximation, once I put that 0 compensator in there, it's, all bets are off. Like, you could have a problem. And that's what happened with the case of the pole at negative 40 that corresponded to 0 at like negative 1 point something.
This is like the point that you're testing is that the real part is around 10, so the 40 will not be 5 times bigger than 10.
Right, but also remember zeros being close by is problematic for us. So a 0 that's right there is really going to affect things. Now, Yeah. So that's my main thing to think of in this case is there's a 0 coming there. The other way to check your second order approximation is to do the simulation and say, okay, like based on my second order approximation, if I put in this gain, like I should get my settling time should be 0.4 seconds and my overshoot should be 10. So in this case, that is very much not true, right? So the second order approximation in this case was bad. Second order approximation in these two cases was quite a bit better, right? It's not perfect, clearly, because if we hit exactly 0.4 and 10%, then we would be right on, and our second order approximation would be very good. But we didn't. It was close, and it happened to be on the good side of close, right? So we didn't get our settling time like 0.45, and we didn't have a percent overshoot of 13. That would have been not great for our results. So it was off in the right direction, right? It was off in the tighter. It was tighter to what we probably want in our design. Usually percent overshoot and settling times are max values. You want to be in the ballpark, though. It's like they always talk about over-designing things. You don't want to over-design something. So if something calls for 0.4 seconds of settling time, you don't want to design it to have 0.004 seconds of settling time, because most likely you're paying for that somewhere. It's harder to have less and less settling time. So you're probably paying for that in control effort, and control effort means you have to get a more expensive actuator, and you have to use more power, and you didn't need to. So that's why you don't want to over-design it too much. And think about this too. If this was, this is just a general design consideration, but if you're designing a controller, hopefully you have your factor of safety built into this, right? So you say, okay, I want my settling time to be 0.4 seconds because, if it was 1 second, or if it was 12, or if it was 1,200 milliseconds, or if it was 3, 4, 5 times what this is, then it would be dangerous, right? So you want to be designing it for, built in that factor of safety there. Okay. Anything else? I realized recently that we don't talk about factor of safety in later engineering classes very much. We talk about it early on, and talk about it as much later on. It's a simple concept, like build it better, by some factor. But sometimes you have to figure out where that needs to go. It should be on the requirements themselves. So there are a lot of nonlinearities here, where if you change something a little bit, and then you take the cube root of it, it's different. So you have to be careful about the functional dependency of your factors of safety. So in this case, if your requirements are in settling time and percent overshoot, that's where you'd want your factor of safety to be, not in, say, the pole location. So say you're okay, I'll move my design point by I'll make it 3 times leftward, so I'll get, according to the second order approximation, I'll get 3 times faster settling time. Well, that's fine, but you got to look at the end what your actual simulation results are. And I would say you want that value to be 3 times, not the root location, not the design point. Your actual performance is what you should be designing toward. Okay. So these are pretty, they're similar to PD controllers, but you just have one extra parameter. And now we've done lead. Well, so today lead, before we did derivative, Before that we did lag. Before that we did PI. Before that we did proportional. And now we just got 2 left, which are essentially putting everything together. And there are no surprises here. I mean, you just have to figure out how to compensate for one thing, then compensate for the other thing without undoing what you did, which is how we constructed these compensators. So it should be fairly straightforward to do this process. It's just another sort of stack on top. So, yeah, we'll pick that up on Friday then. If you guys watch any podcasts, don't send me the titles, please.